the law of motion in his book Principia. Newton stated the following three laws of motion. Newton's first law of motion: a body continues to be in its state of rest or uniform motion in straight line unless a force is applied on it. This law is also called law of inertia or law of Galileo. Note: Galileo in 17th century laid the foundation of Newtonian mechanics, which signaled the birth of modern science. Newton's first law can be understood in the following two parts. Number 1, definition of inertia. Number 2, definition of force. Definition of inertia. In the first part, Newton's first law gives the definition of inertia, according to which an object cannot change its state by itself. If the object is in the state of rest, it will remain in the state of rest, and if it is moving in some direction, it will continue to move with same speed in the same direction unless an external force is applied on it. In other words, we can say that inertia is an inherent property of each body by virtue of which it has tendency to resist the change in its state of rest or state of motion. The property of inertia is because of mass of the body. The greater the mass, the greater is the inertia of body. Thus, a lighter body has less inertia than a heavier body. So we say that mass is measure of inertia. For example, a cricket ball is more massive than a tennis ball. The cricket ball acquires much smaller velocity than a tennis ball. When the two balls are pushed with equal force for the same duration, in case when they are moving with same velocity, it is more difficult to stop the cricket ball which has more mass in comparison to the tennis ball which has less mass. Kinds of inertia. Inertia is of the following two kinds: inertia of rest, inertia of motion. Number 1, inertia of rest. If a body is at rest, it will continue to remain at rest unless an external force is applied to change its state of rest. Example: when a train moves forward, the passenger standing in the compartment tends to fall backwards. This is so because the lower part of the body of the passenger is in close contact with train. As the train starts moving, the lower part of the passenger's body shares the motion, but the upper part cannot share the motion simultaneously, and so it tends to remain at the same place. Consequently, the lower part of the body moves ahead and the upper part is left behind, so the passenger tends to fall backward. When a hanging carpet is beaten with a stick, the dust particles start coming out of it. The reason is that the part of the carpet where the sticks uh, strikes come in motion with the dust particles settle on it, remain in the state of rest due to the inertia of rest. Thus, that part of the carpet moves ahead, leaving behind the dust particles which fall down due to the Earth's gravitational pull. Inertia of motion. A body in a state of motion possesses inertia of motion, and it continues to be in the state of motion with the same speed in the same direction in a straight line unless an external force is applied to it to change its state. Example: a person riding a bicycle along a level road does not come to rest immediately after he stops pedaling. The bicycle continues to move forward due to the inertia of motion, but eventually it comes to rest as a result of retarding action of friction, etc. A ball thrown vertically upwards by a person in a moving train comes back to his hand due to the inertia of motion. A person often runs before taking a jump. The reason is that by running first he brings himself in the state of motion, and then it becomes easier for him to take a jump. When a running car stops suddenly, the passenger is jerked forward due to inertia of motion. The property of inertia is because of the mass of the body. The greater the mass, the greater is the inertia of the body. Newton's first law of motion gives us the definition of force in a qualitative way. That is, a force is the cause that can change the state of rest or of uniform motion of a body. Newton's second law of motion. The rate of change of momentum of body is directly proportional to the force applied on it, and this change takes place in the direction of force. This law relates the force F to mass m and acceleration a of the body. They are related as F equal to ma. Thus, magnitude of force can be calculated by multiplying mass of the body and the acceleration produced in it. Hence, second law of motion gives us a measure of force, unit of force. The units of force are two types. Absolute units and gravitational unit. Absolute units of force on SI is Newton, and on CGS system is dyne. 1 Newton equal to 10 to the power 5 dyne. The gravitational unit of force on SI is kilogram weight or kilogram force. Thus 1 kilogram weight or 1 kg force equal to 1 kg into 9.8 meter per second square, or equal to 9.8 Newton. The gravitational unit of force in CGS system is gram weight or gram force. Thus, 1 gram weight or 1 gram force equal to 1 gram into 980 centimeter square, or equal to 980 dyne. Momentum. The momentum of a body is the product of its mass and velocity. For a body of mass m moving with velocity v, the momentum equal to m into v. It is a vector quantity. It has the same direction as the direction of motion of the body. The SI unit of momentum is uh, kg meter per second, and the CGS unit is gram centimeter per second. Rate of change of momentum equal to force. Impulse. The force which act on bodies for short time are called impulsive force. For example, in hitting a ball with a bat, in driving a nail into a wooden block with a hammer, in firing a gun, etc. An impulsive force does not remain constant but changes from 0 to maximum and then from maximum to 0. Thus, it is not possible to measure easily the value of impulsive force because it changes with time. In such cases, we measure the total effect of the force called impulse. Hence, impulse of a force in a measure of total effect of the force. Impulse equal to average force into time. Or we define it as L equal to F into T, P minus P. Hence, impulse of a force which is a product of average force during impact and the time for which the impact lasts is measured by the total change in the linear momentum produced during the impact. Impulse of force is positive, negative, or zero according to the momentum of the body, increases, decreases, or remains unchanged under the effect of force. Impulse is a vector quantity. Its direction is the same as that of the force. The SI units of impulse are Newton second and kg meter per second, and the CGS unit of impulse are dyne second and gram centimeter per second. Impulse of a variable force is equal to area enclosed by the force curve and the time axis. Application of the concept of impulse. A cricket player lowers his hands while catching a cricket ball. A player do not do so because he allows a longer time for his hands to stop the ball. When a person falls from a certain height on a cemented floor, the floor does not yield. The total change in linear momentum is produced in a smaller interval of time. Therefore, the floor exerts a much larger force. Due to it, a person receives more injury. On the other hand, when a person falls on a heap or of sand, the sand yield, the same change in linear momentum is produced in much longer time. The average force exerted on the person by the heap of sand is therefore much smaller, and hence the person is not hurt. China wares and glasswares are wrapped in paper or straw pieces while packing. In the event of fall, impact will take a longer time to reach the glass China wares through paper and straw. As a result, the average force exerted on the china or glasswares is small and changes of their breaking is reduced. The vehicles like scooter, car, bus, truck, etc. are provided with shockers. When they move over an uneven road, impulsive forces are exerted by the road. The function of shockers is to increase the time of impact. This would reduce the force jerk experienced by the rider of the vehicle. Bogies of train are provided with buffers. They avoid severe jerks during setting of the train. Due to the presence of buffers, time of impact increases, therefore force during jerks decreases, hence the changes of damage decreases. Note: Newton's second law is the fundamental law of motion. The first law of motion is also included in the second law. We can obtain Newton's first law of motion from second law of motion from Newton's second law. F equal to mass into acceleration. If F equal to 0, then acceleration equal to 0. This means that if no force is applied on the body, its acceleration will be 0. If the body is at rest, it will remain at rest, and if it is moving, it will remain moving in the same direction with the same speed. This is the statement of Newton's first law of motion. Newton's third law of motion. According to Newton's third law of motion, to every action there is equal and opposite reaction. The action and reaction are equal in magnitude and opposite in direction. The action and reaction do not act on the same body. If action is on one body, reaction will be on the other body. If force equal to AB is a force exerted on body A by body B, that is action, and F force equal to BA is the same force exerted on body B by body A, that is reaction, then according to Newton's third law of motion, force AB equal to minus force BA. The third law of motion tells us what is the origin of external force on the body. According to Newton's force never occurs singly in nature. Forces always occur in pairs as a result of mutual interaction between two bodies. Some of the examples of Newton's third law of motion: a book on a table. When a book is placed on a tabletop, the book exerts a force on the table, which is equal to the weight of the book. This may be called the force of action. The table supports the book by exerting an equal force on the book. This is the force of reaction. Since the book is observed to be rest, the net external force on it must be 0. This implies that the normal reaction must be equal and opposite to the weight of the book. Walking. While walking, a person presses the ground in the backward direction. Action by his feet. The ground pushes the person in forward direction with an equal force. Reaction. The component of reaction in the horizontal direction makes the person moved forward. Firing from gun. When a gun is fired, the bullet moves forward. Action. The gun recoil backwards. Reaction. Flight of jet planes and rocket motion. The burnt fuel, which appears in the form of hot and highly compressed gases, escapes through nozzle. Action in the backward direction. The escaping gases push the jet plane or rocket forward. Reaction with the same force. Hence, the jet and rocket moves. Motion of boat away from the shore. When a boatman wants to move the boat away from the shore, he pushes the shore with his oar. Action. The shore pushes the boatman along with boat away with an equal and opposite force. Reaction. Fundamental forces in nature. At the present stage of our understanding, physics has revealed that all the forces occurring in different contexts arise from a small number of fundamental forces in nature. Though the origin of derived forces is complex, yet they can be understood in terms of the following four fundamental forces which govern the macroscopic as well as macroscopic as well as microscopic world. Number 1, gravitational forces. Number 2, weak nuclear forces. Number 3, electromagnetic forces. And number 4, strong nuclear forces. Number 1, gravitational forces. The gravitational force is the force of mutual attraction between any two objects by virtue of their masses. The magnitude of the force exerted by a particle of mass m1 or another particle of mass m2 at the distance r from it is given by Newton's law of gravitation. Formula is F equal to G m1 into m2 divided by r square, where G is universal gravitational constant and has the value G equal to 6.67 into 10 to the power minus 11 Newton meter square divided by kg square. The direction of the force on m2 is toward m1. An equal but opposite force is exerted by mass m2 on mass m1 in accordance with Newton's third law of motion. Thus, the two particles exert equal forces of attraction on each other. Some of the important features, properties of gravitational forces are: gravitational forces are universal attractive forces, that is, they exist between microscopic as well as macroscopic objects irrespective of their size, shape, separation and intervening medium. These forces are never repulsive. These are the weakest force in nature. They operate over very long distances, especially when the objects are massive. For example, rotation of Earth around the Sun is due to gravitational pull of Sun on Earth. Gravitational forces obey inverse square law, that is, they vary inversely as the square of the distance between two bodies. Gravitational forces are central forces, that is, they act along the line joining the centers of two bodies. Gravitational forces are conservative forces. The field particle of gravitational forces is called gravitation. The concept of exchange of field particle between two bodies explain law that two bodies interact with from a distance. Weak nuclear forces. The weak nuclear force appears only in certain nuclear processes, such as the beta decay of nucleus. And in beta decay, the nucleus emits an electron and unchanged particle called neutrino. The weak nuclear force is not as well as the gravitational forces, but much weaker than the strong nuclear and electromagnetic forces. The range of weak nuclear force is exceedingly small, of the order of 10 to the power minus 16 meter. The weak nuclear forces are 10 to the power 25 times stronger than the gravitational force. Electromagnetic forces. The electromagnetic forces are the forces between charged particles. When the charges are at rest, the forces are called electrostatic forces. The forces between unlike charges are attractive, and the forces between like charge are repulsive. These forces are governed by Coulomb's law. The charges in motion produce magnetic effects, and the magnetic field gives rise to a force on a moving charge. That is why electric and magnetic forces in general are inseparable. Hence, the name electromagnetic forces. The magnitude of electric static force F between two static point charges Q1 and Q2 separated by distance r in air or vacuum is given by Coulomb's law, where 1 divided by 4 pi equal to 9 into 10 to the power 9 Newton meter square divided by Coulomb square is constant, and 8.85 equal to 10 to the power minus 12 Coulomb square Newton meter square is absolute electric permittivity of free space. Electromagnetic force is much stronger than the gravitational force. It dominates all phenomena on atomic and molecular scales. The structure of atoms and molecules, the dynamics of chemical reactions, etc., are governed by electromagnetic forces. Some of the macroscopic forces, like the forces between two surfaces in contact, force of friction, tension in spring rope, forces due to spring, etc., are also explained in terms of electromagnetic forces. The smallest magnitude of charge found in nature is the charge on an electron or proton, represented as 1.6 into 10 to the power minus 19 coulomb. All charges are found to have magnitude Ne, where n is an integer. Electric charge is therefore said to be quantized. Some of the silent features of electromagnetic forces are: these forces may be attractive or repulsive. Like charges repel each other, and unlike charges attract each other. These forces are governed by Coulomb's law, which are similar to Newton's laws of gravitation. They obey inverse square law. Electrostatic forces between two protons are 10 to the power 36 times stronger than gravitational forces. They operate over distances which are not very large. They are central forces. They are also conservative forces. The field with particle of electromagnetic forces is photon, which carries no charge and has zero rest mass.